This video was inspired by a question on CD from a user who is trying their first attempt at adding feed forward into feedback control for arm angle. And they're not sure if this code they've created might work, how they could test it, how they could adjust parameters. I assume like, maybe the feed forward model parameters to see how those would work properly. And so they're just looking for some advice here. And one thing that you can do is for something simple like a single jointed arm, you can run a simulation and test your code against the simulated arm and, turn around really quickly with changes, no really worry about, no danger of damaging an actual robot mechanism, test everything that you want, get it working in simulation. And then when it's done, it's a pretty simple port to get it over to the actual robot. And so in order to help this, this person, really anybody else who might need help, I've created a little repository with command robot code, just basic skeleton code that implements only one subsystem, just an arm. And that arm has an arm simulation in it, as well as simple feed forward control, as well as profiled feedback control. And so you can test that with your arm and your approach to how this is done. I've implemented one way, but there's lots of other ways that you could implement control, and it's easy to test here. And if you get it working, just port it over. So just a real quick run through on what's here in the arm subsystem. There's a profiled PID controller with tuning parameters. I'm just using proportional and derivative. I'm not going to use integral for this integrating system. And use a trapezoid profile with maximum velocity and acceleration parameters. And then I'm going to use the arm feed forward calculation that comes from WPI Lib and implement the KG, KV, and KA parameters in that. I think the original poster was trying to use the profiled PID controller. I think they also were trying to use their own calculation for feed forward. This looks pretty accurate. But you can do it the way you want it in simulation. That's the beauty of it. If you wanted to put this in yourself instead of using the arm feed forward, you're welcome to test it all. You could even do something like, in the thread, it was mentioned that the KG, sometimes there's some issues depending on, whether your arm, wraps around 180 degrees or not, to whether the KG might start acting in the wrong direction. Some people would rather have the KG be more of a feedback linearization than a feed forward term. So if you wanted to wrap KG into some feedback linearization, put that in, and then just, have a feed forward term that just used, the KV and the KA, you're welcome to test that in simulation, see if you like it. All very possible. So simple control, that's all it would be. The bigger part of this particular subsystem is the simulation of the arm. That wouldn't be the case in actual robot code. You wouldn't have this part. But it's, again, easy to just take out your controller and pop it in where you've actually, you're just going to send the voltage to a controller rather than to a simulation. But for this simulation, I'm just going to simulate with one Neo Vortex and run that into the single jointed arm sim that comes from WPI Lib. In order to run that, you do need this arm gearbox, which represents the motor. It's kind of funny that it's called gearbox. The arm reduction, which sort of is the gearbox, is a separate item. And there's also other parameters that you need here, the arm length, the arm mass, some angles, and all that is currently set up in the constants file. So in this particular case, I'm simulating a planetary gearbox that has 5-to-1, 5-to-1, and 4-to-1 stages together, and then chain drive that's got a 64-tooth driven sprocket and 18-tooth driving. And so that gives you a little over 350-to-1 gear reduction, which is a lot. So the arm's not going to be the fastest, but it's going to not take a lot of current to move either. So that's, perhaps nice. And you can make this whatever you want. If you want multiple motors to really move that arm quicker, a lot less gear reduction, you can set that up. I'm simulating 10 pounds of end effector mass where the center of mass is 20 inches from the pivot. Again, whatever your arm is, you can change those things. I'm simulating going from 34 degrees below horizontal, 0 degrees, parallel to the floor is, that's sort of required for this simulation. The 0 point has to be that horizontal or parallel to the floor position. So this would kind of be a stow or a load position. And then, up to say 100 degrees, just a little bit past vertical would be the maximum angle it could possibly go. And I've thrown a few angles in here just to test, like a shooting angle, raise it to 16 degrees above horizontal, to amp, raise it, almost vertical, 86 degrees, just for example. So you can set up the arm in here any way that you want. I've simulated an encoder in here, and again, in real life, you probably have the encoder that's built into your motor that you're using, but you could use an external one as well. I've thrown in a mechanism 2D display. I'm not going to discuss that in any detail here, but in the smart dashboard, it'll show you how the arm moves. And that's kind of important, I think, in simulation, that you can see what's happening in addition to just maybe watching the data. So the simulation of the mechanism is kind of nice. To create the actual arm, we're not going to do very much here. Just fix up a couple things on the encoder and the controller. Get that arm mechanism put over on the dashboard, and bring some tuning over from a preferences location in network tables. Now, to implement control, this is where you would do something. This is where you test things. And so I'm implementing it in periodic in the subsystem. You may want to do it in a command. You may want to put it in periodic in robot. It's up to you how you want to do it. But I've done it this way. I've set it up so that if it's in closed loop, it does calculations. If it's not, the PID controller is continually being initialized so that the set point is tracking the actual arm angle. And so you can turn it back on at any time, put it back in closed loop, and it just picks up from where it was. Doing some logging so we can see some things in Smart Dashboard. And then here's the simulation itself. Again, this would, if you're putting this in your real code, you don't have to run this simulation. Your robot will do this stuff for you, but I'm just really putting the controller, the total voltage from both controllers goes into the ARM simulator. And then we integrate that simulator at the 50 hertz rate, normal Robo-Rio update rate, to just keep trying to figure out where's the arm every 0.02 seconds. Update the encoder so it's tracking, where the simulator says the arm is, make sure the encoder has that value. And even here, just for fun, I think in most cases, simulate the loaded voltage from the battery with just the arm motor affecting it. Normally, it's not going to be that much from the arm to lower the battery voltage. If you were moving the arm and driving, that's a different story, but we're not simulating driving here. Put the mechanism over, or update the mechanism with the angle from the simulator. And then there's a little method here to just change the goal of the PID controller. So we can just put this new set point in for the goal, and it'll pass it through. Now, goal and set point are different in a profiled PID controller. Goal is the eventual place that you want to go. It's the long-term set point, if you want to think about it like that. And then the actual set point from the profiled PID controller follows the profile, and so it changes more slowly. It doesn't go immediately to goal. It sort of moves over its trapezoidal velocity and acceleration limit path to get from where it is to the goal eventually. So goal is a specific thing, different really from set point in a profiled sense. Got a little method here to just stop the arm, and one to get the tuning from the preferences over to the controller. So that's all that there is in ARM. Robot container is even simpler than that. We just instantiate an ARM, set up a controller so I can push a few buttons to make the simulation move the arm. And then we're just looking at 4 controller buttons here. Whenever those are pressed, it just creates a command to change the goal degrees to whatever I want. So load angle, move it to that, bottom position is A, the shooting angle, that mid position is B, the amp angle, the high angle is Y, and then X would stop it. So it'd put it effectively back into open loop and just let the arm fall down with no motor voltage on it. And so that's really all there is in robot container. And then there's those constants that I showed. And we've also got the tuning constants for the PID loop. I'm going to run with just a gain for this simulation, but you can test, derivative. You could even test integral if you really wanted to. Go ahead and throw that in. And then I've got some initial values for my trapezoidal velocity and acceleration maximums. The 1.8 radians per second for the velocity, that's kind of important that we get that right. You can't just specify any value that you want here. The arm has to be able to actually move that quickly. And so I'll show you just a second how you can sort of see what that maximum really is. Acceleration, you've got some, there are some limits, but they're not as clear cut. And you might have to evaluate what the maximum acceleration is. If you even want to go to a maximum acceleration, you probably, to get a nice smooth movement of the arm, you probably want to go at well less than the maximum acceleration here. So there's just a value to start with. Typically on these things, if you're in the range of 1x to 2x of the velocity for the acceleration, you're probably in the right range in a lot of cases for a single jointed arm. And then the feed forward parameters, the kg, kv, ka, these, and this is actually not, I was testing this, 6.01 is the right value there. You can get these, you can get a decent approximation by using the website Recalc, and that's reca.lc. And inside of Recalc, there's an ARM calculator tab. And if you go to that, you can specify the same thing that we just did to set up the simulation. Running one Neo Vortex, there's a lot of motors that are possible here. What's that gear ratio, the reduction? What's the distance from the pivot to the center of mass? What's the arm mass? So these start and end angles, and that'll simulate the operation of the arm. And in fact, it'll also give you those estimated feed forward values for kg, kv, and ka. And these here are exactly what I have put in the code. And because I'm simulating the arm, the feed forward is going to be really pretty accurate in this case, more accurate than you would expect it to be on a real robot. But I'll show you also a little bit about what happens if your feed forward is inaccurate, but you'll start out seeing what happens if it's very accurate. So that's where those come from, and you can calculate those for your own arm using this calculator. And they work pretty well as long as you put in the right values for the different parameters there. So that's really the whole code base. And at this point, really all that we need to do is simulate it. And so to simulate this code, we're going to use Shift Control P to bring up the palette, and we'll run simulate robot code. And we'll make it a Java simulation. And we're just going to use a simulation GUI to run it. And now this GUI has been, I've set this one up specifically here for this this particular repo, it should be set up like this. If you copy the repo and run it, the JSON files are in there that would set this up. But if it wasn't set up, for plots, these are already set up, but you can go up into plot and create a new plot window and pop a new one up here. When you have plots, you can just click and drag anything that you have from the network tables into these. You can just drag them in. Once they're in, if you right click on one, you can make some changes like what its color is, which y-axis it's going to be on, the weight of the line, that kind of thing. You can change the axis, like this one I probably should change. This one is the one that's going to be the amperage, so I'm going to make it -20 to 60. That'll put the amperage kind of down on the bottom, where in the middle here is more of the voltages, and the voltages are all going to be on this side. That's that. So you can change those kinds of things in here. There's that simulation, the mechanism 2D is showing up here. You can go ahead and bring those things up. So like in Smart Dashboard, I sent that out to Smart Dashboard. If it's not showing, you can go click on it and make sure that it shows up and put it where you want it. For controllers, you can drag the controller over here to like joystick 0, and then it's gonna go ahead and work. So it's not really really how to use this interface, but hopefully it's pretty obvious how to make most of this happen. But we're going to run the simulation, and the way this works is that as soon as we put it in teleop, the way I've coded it, the arm goes into closed loop immediately, and it's going to move it to the load position, which is 3 degrees up from the physical stop. And so it's sitting in open loop right now, not running, it's disabled. And so I'm going to put it into teleop, and it'll immediately go into closed loop, and it's going to stay that way. So we'll put it in teleop. There it goes. It does its move, and we see some behavior here. And so here I'm going to go ahead and press the B button and move it to the shoot position. So there we go. And let's go ahead and pause these and see what's happened. So what has happened is the set point is now changing. We know the goal went straight up to 16. That's where we wanted that to go. So I'm not even showing the goal on here, but it went to 16. But the set point follows a trapezoidal profile that's limited in velocity and acceleration. And so the set point is going up here, which is the orange, and then the actual arm angle is blue. And so it's tracking really quite well with the parameters that we have in here. And we see that we went up on this acceleration level, and we had that maximum of 1.8 radians per second. And looks like we just about touched it here at the top, but maybe not quite. Based on our acceleration, which was 4 radians per second squared, we only went this fast going up on the velocity, and so it never quite reached. But we can change that. I'll show you that in a sec. But then we see how did this arm track the set point, the changing set point. And it did it mostly with feed forward. So feed forward here is the orange color. That's, it looks like that went up really nicely. And the feedback, which is green, had to do almost nothing because the feed forward was really very accurate. So the total voltage is almost identical to the orange. The feedback had very, very little to do. We only ran about 10, 11 amps or so to make this move, simulated amps, based on the acceleration, which is not, it's smooth, not really jerky, and that big gear reduction. So 10 amps is pretty manageable. If the way you simulate starts to get up to, you're pushing 40 amps, you might be hitting current limits that you may have set. The simulation may become a little bit less accurate. I'm not entirely sure with the single jointed arm sim from WPI Lab how I could possibly do a current limit on that. If I was really worried about it, I'd probably have to extend the class. But as long as you keep it, below what you'd set for a current limit, it's going to be really pretty accurate. And even if you exceed the current limit, it's probably still kind of useful to see how that might work at even higher currents. But anyway, so there's that small move just from the bottom to shoot, and we can make other moves and see how those look. So if I went back to the bottom, and then say I went all the way up to the top to where it'd be like the amp position. I'll go ahead and pause that one for a second too here. You can see the trapezoidal velocity profile much, much clearer here because it's such a long move. Now we're limiting out. Our acceleration got us up to that 1.8 radians per second max, and then it holds there. So all in here, it's all going up at 1.8 radians per second. And then the acceleration makes it smooth on the edges. And so we can see that in here. And so we're testing, our control's working. And if you have your own way of doing your control, you can test it here and see if it's working. Just for interest, if I wanted to say, slow this acceleration way down. So let's say I only want it to be 1 radian per second squared. I have to disable in this simulation and put it back in TeleOp for it to pick up the new tuning constants. But so this is up at the top. So if I brought this back down, we can see just how slow that brings it down. And in fact, we never even reached that 1.8 radians per second limit because acceleration was so slow. So very S-shaped. Took what we're looking at 1.5 seconds. Oh no, 2.5 seconds to get down, which is pretty crazy. So we wouldn't want to be going, that slow. We could also go a lot faster if we wanted to. And again, the limit on how fast you could go on the real robot may change. The simulation should be close, but values in simulation should just be a starting point for the real robot, but they should be good starting points. Now that 1.8, acceleration, we can change a good bit. You can make it go pretty fast, but there is a limit to the velocity that you can run. And this 1.8 is pretty close. If I went over back to the recalc here and we look at what's simulated here on recalc, we're going with 121 degrees of movement total in 1.081 seconds. So if I calculate that out, that's like just under 112 degrees per second. And if I change degrees per second into radians per second, divide by 360, multiply by 2 and pi, we get 1.95 or so radians per second max. And so if we went faster than that in the simulation, if we're trying to, oops, not here, there we go. If we said, instead of like 1.8, let's say we wanted 2.8, we're trying to get it to move that fast. Let's disable, put it back in TeleOp. Let's get this running again. Let's go ahead and push it all the way back up to that amp position. And let's see what happened here. So now what we see is, our profile went faster than the motor could actually go. For a while we were okay until we got over the limit of 12 that we could actually get out of the battery. And at that point we veered away. We couldn't go any faster. And so we got this offset, and eventually then we catch back up. The PID assures that we catch back up. But you see how much work the PID had to do here, because, the feed forward isn't capable. It's not, we can't drive this thing up to 17 volts. It won't work. So the PID, the feed forward becomes inaccurate. And we see a sort of a deviation like this. So we can't just set this anywhere we want. It has to be a feasible value. You can certainly set it at less than the max. You know, if it's 1.95 is max, you want 1, that's fine, but you can't make it 2.8. So that's what happens if your velocity is infeasible. You could also look and see what happens if your, say your feed forward parameters are wrong. So we'll put this back on to where it's feasible again. Let's drop it back down. Whoops, let's resume here. So we can see, and then, you know, just to remind ourselves, we go back up and it looks like that. And our PID is doing very little because our feed forward is so good. So in order to change those values, I actually have to change the code. I don't know a way in the ARM feed forward class. There's no way to actually change it on the fly like there is to change tuning constants in the PID controller. But let's say it was 4 here. We chose 4 not knowing, you know, for whatever reason we're inaccurate and it's too low. This KV, we're not asking for enough volts to move at a certain velocity. So we'll go ahead and save that and we'll bring up the command palette again and we'll simulate. Okay, so let's go ahead and pop it back in teleop and we'll just go ahead and do that. We'll do that to big move. So we'll go all the way up to the amp position and pause that. And because it didn't save my thing as I exited it, make sure that's kind of out of the way so we can see better here. Okay. So here we see that the feed forward just did not do enough. The constant was too low. Feed forward did not do enough to keep this running on track. But because we have PID, it says, well, I can add. You know, I realize there's an error, so I have to keep adding. And based on this big proportional gain that we have of 50, it added like this. And so now our total voltage went up to where it needed to go, such that we are, you know, tracking again pretty close. We can see we're a little bit behind. We were actually with feed forward of 6, we were actually a little bit ahead. If you remember, the blue line was a little bit above the orange when the feed forward was 6.01. Now with it too low, we're tracking below. The PID always has to catch up. And so we're going to just be a little bit slower at keeping it on track, but we still keep it on track really well. PID is the P, at least this is just P. The P keeps it where we need it. But you'd like to do as much with feed forward as you could. It's going to give you the fastest response, and it's the way you'd like to go. So that's just an example of what things look like when it's not particularly accurate. And you could use this on the real robot too, that if you track your feed forward and your feedback outputs, you know, if feedback's having to do too much, you know, your feed forward gain for V is probably a little bit low. If you're just trying to hold it out there sideways and not move it, and the PID is running high, above 0, your KG is probably too low. You know, you'd have to increase your KG a little bit. Vice versa, you know, if you're in that situation and PID is running below 0, your KG is probably a little bit big. So you can do these things and help tune your, look at this value and help tune your actual robot as well. So that's pretty much it. So the idea is codebase is here. You know, make it work for your arm, whatever kind of values that you need, but then choose, you know, do I want to do my control in periodic? Do I want it in a command? What do my commands look like? How do I change my set points? Am I changing it, you know, the way we are here where, you know, we just change a value? If you're in a command, you probably have to do something different, like use a supplier to change it. Once the, you know, command has been created, you have to use a supplier to change something internal to that command. You know, different ways that you that you may want to do. You could even just have commands override other commands. One command cancels the previous command as long as the ARM subsystem is called a requirement in there. So, do you have overriding commands? How do you want to do it? You can test it all in simulation, and then once it's working the way you want, moving it over to robot is really, pretty much, instead of having a simulation periodic, where you're sending your voltage to the simulator, just have something where you send your voltage request to the controller, and it's going to run about the same on the robot. And of course, this is also running with the controllers in the RoboRio. If you're trying to run your PID on a Spark Max or on a Talon FX, that's a little bit harder to simulate to get it just right for working. Certainly the tuning parameters are going to be pretty different for those. So you may have a little bit extra work to do if you're trying to run PID in the hardware and run feed forward on the RoboRio. But again, you can try your best to put that in simulation if that's what you really want to do. So hopefully this has been useful to see how to use simulation to be able to test different control strategies.